Hi, I'm Sonu,
I'm Lois.
I'm Lawrence.
I'm Shalika.
and we are SensorDev.
So the goal of SensorDev is to create low-cost sensors to be used in lab or on-site by the researchers or operators, and this is helpful to recognize inefficiencies in the process and help us reduce those.
So this semester we worked on 4 separate sensors, and each of them are in a separate development process. The 4 sensors are the Fluidized bed solids detector, the Submersible sensor, the MAPE sensor, and Marcin's project. So I'm just quickly going to go over each of the current stages that the 4 sensors are in right now. The Fluidized bed solids detector is almost done with testing. We just have to do the calibration curve for that. For the MAPE sensor, we are currently working on image processing for the application. For the Submersible sensor, we are working on finishing testing and then fabrication as well. And for Marcin's project, we are in the middle of designing and testing.
Okay, so the first sensor is a fluidized bed solids detector, and so the goal behind this sensor was for teams that can't use turbidity meters in labs, so if they have a lot of inflow pipes and whatnot, they can use this in their system to find the turbidity at a certain point in time. So here you have 2 pictures of our current component that we've used for testing and for the calibration curve. It's currently sized for a 1-inch diameter pipe, and I'll go into a bit of the parts of the component in the next slide. So first, we have the LED and the light sensor. So they're positioned to be across from each other, so the maximum incident light can be captured by the light sensor. And this is important because we don't want outside light to be getting in. And next, we have the foam layer and the magnetic strips. The foam layer is used to isolate outside light, and in previous semesters, we have found that this is the best method to do that. Magnetic strips are used to fasten the component to a pipe. And lastly, we have the external input headers. So this is used to attach the 3-volt battery to the component, and then we can start testing from that. So this semester, most of the focus was on developing the calibration curve. So on the left, you'll see a picture of our test setup, and our results were as expected in the sense that once you increase concentration, the illuminance levels did decrease, but we had a linear regime only for certain concentration values. So for really low concentration, we didn't have a linear regime. And on the bottom, you'll see the linearized curve fitting that we put to it. And in future, we'll have to implement this with the HRS team and then see what regime they operate in, and then we can do further testing in that regime.
So one of the problems that we're having right now is on site. Sometimes the operators can't tell what's going on. So in particular in the SED tanks, we can't really tell how high the sludge blanket has gotten. So we want to develop a turbidity meter that's submersible that will just do that. So we're working on a long-term project and a short-term project. The long-term project is with the endoscope, which Lawrence will talk about later. And that one is more helpful because it uses an actual camera, so it'll provide more information, and it's used with a phone, so it's more portable. But currently we're working on a short-term version of that, which is really, we just want to see if there's a if we submerge it, if there's a sludge blanket or not. And so basically what we're doing is we're using the same theories that we did in the fluidized bed solids detector, which Rebecca just talked about. If you can see in the diagram, we have the LED opposite of a sensor, and basically we're just seeing how many sediments are in between. Once we hit a turbidity that's very high and we're reading light reading that's very low, we can then tell that we're in the sludge blanket. So basically we've now finished fabrication. And now that fabrication is done, we have to move on with testing. So we're going to develop a calibration curve, which we've already done in the previous part with the fluidized bed solids detector. So it's going to be very easy, very simple, and will not take that long.
So the sensor I'm working on is the MAPE sensor, and it's basically a more polished long-term version of the submersible sensor that Lois worked on. MAPE stands for Mobile Application Processed Endoscope, and it is basically a sensor that consists of 2 parts. It consists of an endoscope and a mobile application for Android. The endoscope is basically a small camera that is attached to a long wire, and it can be lowered into the sedimentation tank, and it will take images of the water to process for turbidity readings. So the second part of the sensor is the mobile application, and that is what I am working on this semester. The mobile application will basically connect the endoscope to the smartphone and then display the live feed from the endoscope on the smartphone display. And from that, we can capture images continuously as the sensor is being lowered into the sedimentation tank. And then we can process the images using the application for the average light intensity of each pixel. And then from that data, we can convert the light intensity to turbidity readings. And that's pretty much it for the MAPE sensor.
This semester, we also started a new project, which is Marcin's PhD project, and we're helping him build his own turbidimeter. And this project has two main aspects. The first one is the 254 nanometer wavelength. This is ultraviolet light, and we've discovered that this is the wavelength at which the most of the organic matter absorbs the light. And we want to research this further into the future and see how important it could be in our measurements. Our second aspect is the one that we're focused on right now, which is to incorporate two sensors instead of one in our turbidimeter to account for both transmittance as well as absorbance. And our final goal in this case is to measure turbidity at each step along the water treatment process to see where we might need some improvements. And the sensors we're working with right now are infrared, and they're about 850 nanometers wavelength. So the old model of our turbidimeter has a sensor on one end and the light source on the other end of the sample, and the light goes from the source through the sample and to the sensor, and this would only be the transmitted light. But the problem with this model is that we don't know what's happening around the sample and whether the light is being scattered or absorbed. And so we need to account for the absorbance of light as well, because at higher turbidities you might need more precise measurements. So our new model has another sensor at a right angle from the light source. So this would measure two types of light, which is this transmitted light as well as the scattered light. And at higher turbidities, there's more scattering. So the second sensor will have more light at it, but at super high turbidities, most of the light will get absorbed by the sample, and so we need two sensors instead of one to differentiate between the higher turbidities.
So far we've given you a brief overview of the projects that we've had, but now I'm going to talk about the future tasks that we have. So for the fluidized bed solids detector, we've finished fabrication and testing, and we've developed a rudimentary calibration curve. So now we have to work with the HRS team to, like I said, see what parts and specifically what concentrations we need to focus on. For the submersible sensor, we've finished fabrication, and so we're going to be moving into how we're going to take the signal that's being read into, and we're going to convert that into turbidity reading that we can then use. For the MAPE submersible sensor, we have a lot more to do. We have to fix the exposure settings for the endoscope camera. We have to process images for light intensity, and then we have to develop the user interface for the app itself. And then, last but not least, for Marcin's project, we have to test the IR sources and the sensors, which we've recently gotten. And then we're also going to program the Arduino to then take in the SD reading and write to the SD cards.
Thank you for listening, and if you have any questions, feel free to reach out to us on our emails.